Okay, let's continue. So that was set covering. Now let's talk about the maximum covering problem. The problem is very similar. I give you a set of demand I and a set of locations j. The distance dij, or yeah, you can say it as the traveling time, it doesn't matter. And the service levels s, and the covering coefficient aij's are all given. So this part is the same as the set covering problem. You know for each pair of I and j, whether I can be set to cover xj as to cover demand I. Okay, so that's something you know. Now, we don't need to cover everyone, but we are restricted to build at most P facilities. Okay, P is a positive integer. You are given that you can build at most five facilities or seven facilities to cover as many guys as possible. So we want to allocate at most P facilities to cover as many demands as possible. Very quickly, let me review the idea for you. Suppose, let's say we are talking about this slightly different example. Okay, you have three facilities and four demands. Now, if you are given that you need to allocate exactly one facility, then the problem is very simple. You select this one, then you can cover one, two, and three demands. Okay, that's the optimal solution when you can build only one facility. When you have multiple facilities, the problem gets harder. Okay, because even if you cover one demand twice or three times by three different facilities, that does not help you in the sense that you want to cover as many demands as possible. Okay, so whether you want to build this facility depends on whether you have built other facilities. When we are talking about the P equals 2 case, there are multiple optimal solutions. For example, I can choose this one. Okay, with these two facilities, now I can cover everything. Or I can choose to build facilities at here and here. Okay, this is the case that I also cover everything, even though for this particular demand I cover it twice, but it doesn't matter. Well, all we care is whether a facility is covered by any facility, by at least one facility. Okay, so the two ways, okay, to choose this two or to choose that two does not matter. And you can see that the benefit of choosing this facility, we can say that it decreases when you want to build this facility. Okay, because this has been covered twice. So anyway, uh, for a general problem, you just cannot consider different facilities separately. You need to take all the relationships into consideration at once. So that's why this problem can be hard when there are too many facilities and too many demands. Well, the same thing happens to set covering. Alright, we still want to formulate this guy as an integer program. So we still need xi and xj's as our building facility decision. Now we also need to keep a record on demands. For each demand, we need to know whether it is covered or not. Okay, so that yi be that decision variable. Both of them should be integers, I mean binary variables. And then the only difference is here. Previously, this number is 1 for set covering problems. Okay, and now for maximum covering, this is yi. And yi can be 0 or 1, so that means you are not required to minimize a story. You are not required to cover everything. Okay, well, you are allowed to leave some guys away. But what you want is to maximize the total number of covered demands. Okay, so if possible, you're going to try to set all those yi to be 1. Oh, but there is a constraint that is missing here. For this particular problem, the reason that you cannot cover all the demands is because the sum of your total facility built can be at most P. Okay, can be at most P. So with this restriction, the problem gets harder. You probably want to ask whether we need to replace this by equality. I would say no, because for general problems, if you are not able to cover everything, then this inequality will be binding at an optimal solution. So it doesn't matter. Or if you want your formulation to be as general as possible, then you should leave it to be inequality, so that if you can you don't need to build everything to cover everyone, then this also takes that possibility. Okay, again, you have that weighted version. So this is your maximum covering problem. The last type of problem that we want to introduce in this video is the fixed charge location problems. So again, you have a set of demands and a set of locations. Now, at each demand I, you care about one thing called the demand size. Now you can think it as the number of people living in that particular city, or the number of demands of a particular product at a convenience store. Okay, so that's your demand size at demand point I. The unit shipping cost now is a factor. We use Dij to denote the unit shipping cost from location J to demand I. So what's that? That means there is a demand there. There is a number of items that I need to deliver to that particular demand node. And if I do that, I need to pay shipping cost. Okay, I need to pay shipping cost. And that shipping cost typically is proportional to the distance or to the traveling time. Okay. What I also care about is the fixed construction cost at location J. Okay, that's a given number Fij. The question I want to ask is, how may I allocate some facilities to minimize the total shipping and construction cost? Okay, well, I am talking about two kinds of costs. If I build a lot of facilities, okay, then the shipping cost would be smaller because the distance between facilities and demands will become smaller. But then I need to pay a lot of construction cost, so that's not good. Okay, so let's go back to our favorite example here. In this problem, now we don't really care about covering a demand. Okay, covering or not does not really matter. Now we care about whether we want to assign a particular demand to a particular facility. Okay, and that assignment matters because we will ship products or we will travel between that along that route, so that corresponds to costs. Okay, here I just want to show you that suppose I choose to build a facility here. Okay, that means I'm going to deliver products along this way, and this way. Okay, how about this demand? Oh, previously, when we do not have a link here, that's because the distance is too far and the Dij is larger than S. Okay, but now we don't have that service level issue. So actually, between every city and every supply node, there is a link. Okay, so your network would be something like this. So that's the first difference. And now, if you select only the facility in the red cycle, you are going to ship products along these four links. Okay, and that's of course one alternative. But if you say, let's say, also build a facility here, then probably you can use these two routes to serve the lower two consumers, and you don't need to ship products along the two crossed links. Okay, that means if you build more facilities, you can save shipping cost. But of course, the trade-off is that you pay more construction cost. Okay, so this problem is to finding the best balance between shipping cost and the construction cost. So regarding formulating the problem is not very complicated, but you need some more. We still need to decide at each location whether we want to build a facility. And now for each demand, you need to decide who should serve that demand. So Yij is 1 if you use the facility at location J to serve the demand at location I. Okay, so that means there is a link, there is a selected link between that two nodes. Once you make these two decisions, your formulation is to minimize the total shipping cost. Okay, shipping cost and your total construction cost. The second part is the construction cost. Okay, not very difficult to understand. The first part is the total shipping cost. For each facility, for each demand, you need to assign it to one of the facility. And once you do that, your Yij would be 1. Okay, and then you need to pay the cost, Dij, and that's the unit shipping cost, and the Hi is the total demand there. So you need to multiply Hi with that particular Dij to be your total cost. Okay, so very quickly you realize that one constraint is missing on the slides. One thing that you also need is that for each facility, for each demand, I need to make sure that I assign at least one facility to him. Okay, and assign one facility to him. And now it doesn't matter whether you write it as an equality or greater than or equal to. This constraint that I forgot to put on the slides is that for each facility, for each demand, you need to assign one and exactly one facility to serve it. Okay, you don't really need to make this as a greater than or equal to, because you don't want to make two redundant deliveries. Okay, deliveries. The last constraint that we need to pay attention to is this one. Okay, for each Ij, we can use facility J to serve demand I only if that facility has been built. Okay, so if Xj is 0, Yij must be 0, because you cannot use facility J, or because facility J is not built, so facility J cannot serve demand I. Or if Xj is 1, then you are allowed to do that. Okay, and then you decide whether you want to do that or not according to the distances. So that previous model is the uncapacitated version. That means a facility can serve any amount of demand. If facility at location J actually has a limited capacity Kj, then we can add the following capacity constraint here. Okay, When you assign demands to facilities, you cannot simply assign them without considering capacities. Instead, you need to make sure that the total demand assigned to a facility does not exceed its supply. Okay, here you don't have this term. So it's for each facility, you sum up all those demands that has been assigned to it, and you sum up those demands there. The capacitated version is usually called the capacitated facility location problem, abbreviated as CFL, and the uncapacitated version is typically called UFL, uncapacitated facility location problem. Now you have three kinds of facility models. We want to ask whether we want to use this one or that one. So there are, of course, different applicabilities according to your problem. When would you use set covering? When you are required to take care of almost everyone. Typically, when you are playing the role of a government. For example, you want to build fire stations, you want to build police stations, and you need to take care of everyone in your country. Okay, then set covering is something you need to do. Sometimes you want to do maximum covering. That typically happens when you have limited budgets and when you want to, for example, make money. So it's more like a business decision. You want to build, for example, cellular data networks so that most of your country, of the territory, is covered. But you don't really want to cover every single point in that particular region if that does not generate revenue. Finally, when do you use fixed charge locations? That of course happens when your service costs depends on distances. If you are really building warehouses or distribution centers, then UFL or CFL should typically be better than maximum covering, okay? Because you are talking about shipping costs versus construction cost. But if you are building, for example, retail stores, okay, then customers only go to the retail stores that are close enough to them, and they pay their own shipping cost. So you only care about the issue for you is you need to make sure that your retail stores are close enough to them. That means cover them, and you don't care about the cost there. Okay, so you can understand that there are different situations to use different models. All the three problems are NP hard, so that means given large instances, it really takes time to obtain an optimal solution. Many researchers try to look for effective heuristics to solve these problems, but unfortunately we don't have time to talk about them. So, given a facility location problem, as long as you know how to use integer programming to formulate it, then it's a good starting point. If your problem is not complicated enough, then a solver can solve your problem. Or if your problem is of too large scale, you can design your own rule or your own ways based on the help of your integer program. Okay, that's it. Thank you.